Welcome to the second video that accompanies the notes for example 2 for deflections and rotations. This video is going to go through turning the shears into moments equations for the beam shown. Those shear functions give us this shape, which starts and ends at 0, which is good because we have a pin on one end and nothing on the other end, and just one discontinuity due to a point load from the roller at B. Now, because we want to find the rotation and the deflection, what we're going to look for is we're just going to keep integrating, more or less. So we want the moment, and the moment is the integral of the shear function. Integrating this first shear function, we're going to have that the moment that goes from A to B, which is a function of x1, is going to be the integral of our shear function, which is 6 kips minus 1.5 kip per foot times x1. Why can't I make x's and d's? Which is going to be 6 kips x1 minus 1.5 kip per foot divided by 2 x squared. Similarly, the moment, oh dang it, I'm out of space, plus C3, constant integration, the third one. The second one we didn't show much of, but it's there. And from B to C, which is going to be a function of x as well, that will be the integral of 4.5 kips minus 1.5 kips per foot times, this time it's x2, starting over at B, which is going to be positive 4.5 kips x2 minus 1.5 kip per foot divided by 2. That got a little bit away from me. x2 squared plus another constant of integration. Now, to determine what our constants of integration should be, we need to look at the boundary conditions of our beam. At A, we know that we sure as heck can't have any moment because that's a pinned end. So if we pop 0 in for x1, we need to get 0. Well, that's going to right away just tell us that, well, C3 has to be 0. So that goes to 0. And then we have C4 finally. So there's a couple of ways we can go about this. Both of them will work fine. The first thing we can do is just say, well, we'd better have no moment at C because it's a free end. So we can pop a 3 in for x2 because x starts over at B, and that will give us, let's change colors, that'll give us 4.5 kips times 3 feet minus 1.5 kip per foot divided by 2 times 9 square feet plus constant of integration c 4 equals 0. And that's going to give us, it's going to give us that C4 is equal to negative 6.75. And that's in kip feet. Alternatively, we can point out that the moment at B is the moment at B. There's no point moment applied at B that will give us a discontinuity in that moment. So we could also say that the moment at x1 is 9 feet to this equation up here has to be equal to this equation at 0. And that might be even easier, although this is pretty easy as well. Either way, we will end up with the same constant of integration.